Welcome back to 5-Minute Chemistry. Today we are going to be talking about ionic compounds. So for the formation of an ionic compound, we will be drawing an energy diagram. So from the energy diagram, we will start from the elemental forms of sodium and chlorine. So sodium is going to be a solid here. That's why we have the letter S in parentheses next to the symbols over there. And we will have chlorine as a gas. That is what the G next to the symbol stands for. And sodium is a metallic solid and chlorine is a diatomic gas. And in this example, I will have 1 mole of sodium and half a mole of chlorine gas, but it's a half a mole of a diatomic molecule, so the number of atoms should be the same, 1 mole, 1 mole. And so the first process here is we have to evaporate the solid, so we need to put in a lot of energy to move all the atoms from the solid phase into the gaseous phase, because just ionizing solids is not that easy to conceptualize. We want to talk about ionizing all the atoms in this sodium we have, and for that we need all the atoms of this sodium to be independently moving, which is a gas phase. Next step, we will break the bonds in the chlorine molecule. So instead of having the diatomic chlorine molecule, I want to have the chlorine as a single atomic gas. So I want to atomize it. I want to break the bond between the chlorine atoms here, and we will get sodium gas and chlorine gas. Both of these processes require us to put in energy to increase the potential energy and increase the kinetic energy of these atoms. So now they are both gas and they can both move freely. Now, next thing is we need to remove an electron from the sodium atom. So if we want to remove the electrons from the sodium atoms, that will require another large amount of energy. So we have to overcome this very strong electrostatic force between the nucleus of the sodium atom and one of the electrons. And once that happens, then we have the ionized sodium in the gas, and we have the free electrons, and we also have the atomic form of chlorine. So next, this electron can be captured by the chlorine atoms and become a chloride ion. So the electron can lose some of its potential energy by moving closer to the chlorine atoms, and this will result in a gas with sodium cations and chloride anions in it. But now we have positively charged and negatively charged particles, so if they get closer to each other, then they can reduce their potential energy by a lot. And this is how the sodium chloride solid will form. So instead of having the freely moving ions in gas, we will have a solid in which the positively charged sodium ions and the negatively charged chlorine ions will be stuck together. And here, this last step, if we would want to reverse it, that is going to be called the lattice energy. Remove all the attractive force between the sodium and chlorine ions. That energy that is required to do that is going to be called the lattice energy. So this lattice energy is quite huge. You can see that even though to create this ionic compound from the elements, we had to put in a lot of energy just ionizing the sodium, and we don't really get the investment of energy back just by the electron being captured by the chlorine atoms. To get the energy investment back, the actual ionic solid compound has to form, but because this lattice energy is so huge for the sodium chloride, you can see that the sodium chloride is at a lower energy state than the elemental sodium and elemental chlorine gas together, which makes it an energetically preferred state of matter. So this is why you can find a lot of sodium chloride in nature, but not really chlorine gas and sodium metal. So how does this sodium chloride compound look like on the atomic scale? What is the structure of these ionic compounds? Well, from the physicist perspective, these compounds are held together by electrostatic forces, but in chemistry, we like to call whatever holds atoms together, we call those things bonds, and in this case, these are ions that are held together, so we call it ionic bonds. And there are no molecules in the modern sense in an ionic compound. Based on the definition by Avogadro, one could try to come up with a smallest division of these ionic compounds that would still keep the chemical properties, but we don't really consider that in ionic compounds, because if you just take a look at this two-dimensional cross-section of an ionic crystal here, you can see that this cation here has in this one plane 4 negatively charged anions next to each other, which it has a strong interaction with it. And if you imagine this in 3 dimensions, there should be one more negatively charged ion behind this positively charged cation and one negatively charged anion in front of this positively charged cation. So in total, there should be 6 other ions. This one ion is direct contact with, which has an ionic bond with. And the anions here also have the same situation, but with other cations. So we cannot really make any subdivision here in these ionic compounds to designate molecules. It's a crystal lattice in which every cation is bound to its neighbors, and then those neighboring anions are bound to their neighbors. So there is no natural subdivision here. So that's why we say that these solids, there are no molecules in them. And therefore we don't have molecular formulas for ionic compounds. We have only empirical formulas, but that's not a problem because we can use the empirical formulas to calculate moles anyways. Okay, so that's it for today, and I will see you tomorrow.